All right, chemistry. We're back at it. Um, it's been a little bit, right? We had break. We've had a few days here, right? Hopefully you saw my Tuesday update. Um, it is now Thursday. I'm getting to making the video for quite a bit here, right? So it's been the last couple days. Today it will be tomorrow and a bunch of next week as well, like up until basically next Wednesday. So the notes that we're going to be picking up with, if you remember, we left off with some of electrons. We left off talking about redox and Leo Szgür, Anox, Red Cat, electrochemical cells. So we left off with that and with periodic table trends. So looking at hello, there we go. Looking at the periodic table, looking at trends, specifically like how the groups are related and what is similar there, how the periods are related, how to read the next couple pages. So that's page 9, and then page 10 and 11 have the kind of extra information on the periodic table elements. What I want to pick up on here, right, is page 78. I just made a new little whiteboard thingy here. And we have page 78 going all the way out to page 84. There's also a lab, possibly two. It might not be this one. There's another lab that I'd like to do that I don't have I don't know why, but I don't seem to have the sheet for it. But there is another lab that I'd like to do in the next week or so. It might go up next Wednesday for fully remote students. So your lab might go up next week, the week of the. It's the 9th today, so 10. It's the 9th. It's the 8th today. What day is today? Losing my mind. It's the 8th today, so the 9th is tomorrow. That means 10 Saturday, 11 Sunday, so that the Monday the 12th, so Wednesday the 14th, you'll definitely see another video. You might see two labs in that video instead of in this video, which is not a big deal. It kind of depends on how I get to it during class, but at the very least, fully remote students, I want you guys to have the same notes, the same little added stuff that the kids who are in class have. So let's pick up here on page 78, talking about bonding. Right now, the reason that bonding exists in the electron section is because all bonding comes down to electron interactions. What happens when one atom and another atom come close enough to each other that their electrons interact and they possibly stick and bond to each other, right? So the biggest reason, like the 100% biggest reason that any atom bonds to another atom is because, and I think I probably want to have a slightly smaller, an atom becomes stable. It's all about stability, right? An atom becomes stable when it acquires the electron configuration of a noble gas, which is 8 valence electrons, or something that we call an octet, right? Octet, kind of like a quartet is a group of 4 people who do things. An octet is a group of 8 valence electrons. Now, electron configuration is something that you can find on the periodic table. The noble gases are a specific group. They are group 18. So these gases here, if we look at them, they have electron configurations that end, right? The last number here is 8. So their electron configuration ends with 8. That's what they look like. So when atoms bond to other atoms, clarity is just a little weird there. It's a little better. But anyway, atoms will become most stable when that last shell is filled with 8. Now, there it is. There are some exceptions. I'm not terribly bothered about like the 2 exceptions that are listed. The big exception that you should be aware of, like a little asterisk here for yourself. Hydrogen, which is H, can only hold 2 electrons. Right, that's kind of the biggest one that might be a red flag. Hydrogen is so small. It's only one proton. And the reason electrons stick around is because they're attracted to the protons in the nucleus. But because hydrogen only has one proton, it can only hold on to a max of 2 electrons. It's kind of like only able to juggle those 2 electrons. If you try to throw a third one at it, it's going to drop one of them. It'll only hold 2, right? As a system, as an atom, as a group of atoms, as a compound, right, becomes more stable, talking about stability, its energy decreases. So the energy is going to go down. And that comes back to, I had said before in, I think, the thermochemistry section, nature is lazy. Nature wants to be as low energy and high entropy, right, messy as possible. Lazy and messy. That's what we're looking at, right? The fact that when bonds form, right, when we form a bond, energy is actually released, which makes bonding an exothermic process. You should notice that the next bullet point is the same, right? So as energy is absorbed or gained, breaking bonds is endothermic. And my best kind of like example or analog for that is if you want to chop down a tree, the tree is like bonded to the earth or a branch is bonded to the trunk, you need to put in some of your energy to like hack at it and take it away. Or if you want to rip 2 things apart, you have to use some of your own energy and put it into the object that you're ripping apart. So absorbing or gaining energy is an endothermic process. Breaking a bond is an endothermic process. Now, there are 3 main types of bonds, and if you look further on the sheet, you'll see that ionic bonds and covalent bonds are 2 of them. All right, so those are the bigger 2, ionic and covalent, right? And those are also our 2 types of compounds. But there's a third. It's metallic bonding. And metallic bonding happens in individual metals. So if you have a chunk of copper, it has metallic bonding. If you have a piece of aluminum, it has metallic bonding. If you had a gold bar, it has metallic bonding. But that's the only place it will show up. Metallic bonding is called metallic bonding because it only exists in individual metals. If you try to combine, several metals, you create an alloy, which is a mixture. You will still have metallic bonding, but because you haven't created a new chemical, the 2 elements don't like mix in exact proportions. It's still only a mixture. You still have the metallic bonding of one metal and the metallic bonding of another metal. What you're doing is kind of like twisting them together. All right. So let's talk about ionic bonding first. And again, these videos from here until the end of the year are going to be a bit longer. So if you need to kind of break it up into little sections, I'll try to have like timestamps in the description so that you can like skip ahead to the part that you need. But let's talk here about ionic bonding, which happens between a metal and a nonmetal. And hopefully you remember that from way back in the beginning of the year, identifying different types of compounds. Ionic compounds had a metal and a nonmetal, or they have a polyatomic ion, right? But the big deal is that they form when there's a transfer of electrons. Electrons actually move from one place to another place, right? They're shifted from one atom to a different atom, and that's why they become ions. They have a charge. The pair of ions is created, and they have opposite charges. One of them will be positive, the other will be negative. They attract strongly. That opposites attract premise that you have had in your science classes over the course of many years is very important here. The attraction of oppositely charged ions is simply called an ionic bond. If you actually want an electron transfer to occur, then what you need is one atom that's able to lose electrons readily. They have low ionization energy. They have low electronegativity. Ionization energy is literally how much energy does it take to rip an electron away from this thing. So if it's a low amount, it's very easy to lose it. Additionally, hopefully you remember, electronegativity is the attraction for electrons. So if that is low, then it really doesn't care about losing that electron. So you need one atom that's easily able to lose electrons, and a different atom that's easily able to gain electrons. So the one that's able to lose will have it yoinked away by the one that's easy to gain. And remember again, electronegativity is attraction for electrons. There are two more bullet points here that have interesting characteristics. The characteristic I want you to focus on, or one of the characteristics that you should be able to associate directly with, like, oh, this is a characteristic of an ionic compound, is the fact that they have high melting points. Having a high melting point is a strong characteristic of a compound being ionic or of a compound having ionic bonds. And when I say high melting point, I don't mean like 100 or 200 Celsius. I mean like 600 to 700 Celsius. Extremely high melting points, right? Okay, so that's ionic bonds again, in a nutshell. Next, we have covalent bonding. It kind of skips between page 78 and page 79. Covalent bonding, you should notice, it's between two nonmetals, which is the same criteria that we had for covalent compounds. They're compounds that are composed of two or more nonmetals. These nonmetals don't have a really strong tendency to transfer electrons back and forth. They complete their valence shells, or form an octet by sharing electrons, right? Covalent means that they're sharing electrons from the valence shell. It's cooperating valence shells, covalent. All right, and when electrons are shared, we call them covalent bonds. That shared pair, and I'll reiterate in a moment that it's a pair of electrons, but it belongs to both atoms. So when we're counting out, like, does it have 8 valence electrons, we get to double count them. All right. Here at the top of page 79, electron sharing in a covalent bond or in a covalent compound will always occur in pairs. It's always 2 electrons kind of back and forth. All right? You're never only going to have 1 electron that just shifts. It will always be 2. You'll always, and they'll just spend a little bit of time going back and forth, right? If you share 2 electrons, it's called a single bond. If there are 4 electrons going back and forth, then we call it a double bond. If there are 6 electrons going back and forth, then we call it a triple bond. So if you share 1, 2, or 3 pairs of electrons, you will form single, double, or triple bonds, respectively. Right. Now, when usually, like traditionally, when you talk about sharing, if this atom has, 1 atom to share on this, or 1 electron to share, this atom has 1 electron to share, then they'll just like constantly go back and forth, right? That's not entirely true in covalent bonds. Sometimes one of the atoms is a little needier and greedier than the other. So it will keep the electrons a little more frequently. Occasionally, it will share them, but it will demand them back very quickly. It will say, I would like these electrons more often than you would. And the other atom is just like, yeah, okay, that's fine. Right? So when I say the degree of sharing, I mean like the consistency. How often are the electrons on one atom versus being on the other atom? So if electrons are shared equally between 2 atoms, which again just means that they are spending equal amounts of time going back and forth, right? They're not being hogged by one of the elements. Then the bond formed is considered what we call a nonpolar covalent bond. If electrons are shared unequally, then we have created what we call a polar covalent bond. And I'm going to use the example. I've been doing this thing like flashing my, so I have 2 fingers up on this hand, I have 0 fingers up on this hand, right? So let's say these 2 electrons, which represent a pair of electrons, are being shared between these 2 atoms, right? My 2 hands represent 2 different atoms. if they're shared equally, it basically means that we're constantly going back and forth. But because they're going back and forth so fast, let's just treat it like there's one electron on either side. Well, this electron is negative and this electron is negative, and if that's the case, right, they're constantly going back and forth very frequently, then everything is kind of like equally negative, if that makes sense. Which means that it doesn't have poles, right? When we talk about something being polar or non-polar, it either has poles or it doesn't have poles. We talk about... I feel like the only time I've ever heard polar outside of chemistry is talking about a polar bear, right? Polar bears live at the pole, either the North or South Pole. I don't remember which one. I know penguins live at the South Pole. I want to say polar bears also live at the South... No. Oh, polar bears are definitely at the North Pole, because there are polar bears in, like, Iceland that get trapped on ice. Anyway, polar bears live at the pole. The Earth has a North Pole and a South Pole. Bonds and molecules can have positive poles and negative poles. So if we're talking about these electrons being shared, when they get shared unequally, when the electrons spend more time in one place than another, and these electrons are negative, that means that this side of the compound is negative, and this side of the compound is positive. Well, that means that I have a negative pole and a positive pole, which means that my bond is polar, because the electrons spend more time on one side than do on the other. So one side tends to be more negative than the other. Right? That's what polar, covalent, or non-polar means. Right? If you have a compound, this last bullet point kind of relates to both ionic and covalent bonding, but if you have a compound that contains something special, which hopefully, again, you remember this term, a polyatomic ion, and those are found on table E of your reference table, then polyatomic ions actually contain both ionic and covalent bonding. It has ionic because the polyatomic ion is an ion, but it has covalent because the polyatomic ion is held together by little covalent bonds. We'll talk a little bit more about that in, 15 minutes here, but yeah. Now this next little segment is not something that I'm terribly worried about right now. Not because it's not like chemistry important, but because it's a little more in depth than I need to get to, so that you understand kind of how bonding works, and how the differences between ionic and covalent, and even the differences between polar or nonpolar. I may double back to it before the end of the year. I may come back to it before the final exam. But for right now, I'm okay with kind of moving ahead. We won't do that, and we won't have the little practice. I'm intentionally not crossing it out entirely in case I do want to come back to it. But Lewis structures are very interesting. Now, Lewis structures are similar to Bohr diagrams, which we did much earlier in the year. And then we doubled back to. Now, if you remember, Bohr diagrams have like the circles and the dots on them. Lewis structures are nicer because they always show valence electrons only, which means that instead of showing every single energy level that might be in an atom, they only show this last one. They only show the last shell, the outermost shell, the valence shell. All right? There are things for ions, again. I will come back to it. What I'd like to do is take this information of Lewis structures showing valence electrons, and I'd like to start creating some Lewis structures for covalent compounds, and for polyatomic ions, but mostly for covalent compounds, right? Now, again, to reiterate, Lewis structures always show only valence electrons. Only the valence electrons, because it's much simpler. If I was doing the Lewis structure for something like carbon, it's... Ooh, I didn't want you to auto-complete that. Please, no, undo. Go back. Oh, wait, what? Okay, there we go, carbon. So first I would start with the symbol for carbon, which is C. Then I would go to the periodic table, I would go to carbon, I would see it has 4 valence electrons. Well, that means that I need to draw 4 dots around carbon. Generally speaking, I like to go 1 on the top, one on the right, one on the bottom, and one on the left. If I needed to draw the Lewis structure for sulfur, then I would start with the symbol, which is S. Sulfur, if you saw, has 6 valence electrons. So I'll go 1, 2, 3, 4, 5, 6. Right, I just go around clockwise, and I double up only after all 4 sides are full. And you'll see why, like, I kind of do top, right, bottom, left. It has to do with how things bond with each other. Things will bond kind of like this, or like this, or like this, right? We have these, like, sites. We have bonding sites, basically. But Lewis structures are literally just draw the symbol of the element, draw an appropriate number of dots representing the electrons in the valence shell. Ideally, every element wants to look like, argon. Argon has 8 valence electrons, which means that argon is going to be Ar. It's going to have 1, 2, 3, 4, 5, 6, 7, and 8. Right? This would be a completely full valence shell. It has 8 electrons that are paired off, 2 on the top, 2 on the bottom, 2 on the left, and 2 on the right. Carbon is not quite full. Sulfur is not quite full. As such, carbon and sulfur tend to try to bond with other elements so that eventually they can get to 8 valence electrons. Now, there are lots of rules here. It's not really that many. It's like 3.5, 4 rules here. But it's easier to show you the rules than it would be to, like, simply read through these rules. So what I'm going to do is I'm going to use a couple of these simple molecules as examples for how to talk my way through the rules for drawing the Lewis structure, not just for a single atom, but for an entire compound, right? Now, the first one I'm going to start with is the first one down there on page 80. It is CH4, right? So this is 1 C and 4 H's. Because there's only 1 carbon, whatever element has the fewest atoms in that compound, that element is going to be our center point. It's going to be like the linchpin that holds everything else together. And as such, I will draw it kind of like in the center, right? And then the 4 hydrogens are going to go top, bottom, and they're going to go left, right. Let me give myself a little more room here. Now, if you're following along, you might want to wait until this is, I'm going to say, cleaned up, because it can get a little messy. Right. So now that I have drawn the symbols, what I need to do is figure out the valence electrons for each of these elements. Now, I just said carbon has 4, so I'll go 1, 2, 3, 4. And if you check your reference table, you look at it, you would see that hydrogen has 1 valence electron, which means that each of these hydrogens will have 1 dot. And I said I would start at the top, and this is why it's going to get messy. First step is figure out what goes in the middle, it's what there's the least of. Second step is draw the electrons, so create Lewis structures for each individual atom, each individual element. Then, connect the dots. Connect a dot from each outside element to the center element. So I'll put that. That's a line, and that's a line. Oh goodness. Nope. Oh, I see what happened. No, there we go. It thinks it's a triangle. That's cute. Let's do that. Let's do this. Stop it! There we go. Let's do this, and like that's kind of awkward, but okay. Now this looks messy, right? Each hydrogen is bound to the carbon because they're connected by a line. By the way, the line represents 2 electrons that are going back and forth very quickly. They are being shared, right? So they're kind of like being juggled back and forth between the 2. Again, it's this deal, right? They're just going back and forth. What I'm going to do is I'm going to clean up this whole picture. Clean up this picture. I know that carbon is in the middle. I know that the 4 hydrogens are on the outside, and I know that they're going to be connected by a pair of electrons. Now, if I look at this, if you kind of focus on carbon and all the electrons around it, carbon has 1, 2, 3, 4, 5, 6, 7, 8. Remember, each line represents 2. Carbon has 8 electrons. That's good. Carbon is happy. If I look at hydrogen, and I look at the electrons that are attached to this hydrogen, it sees 1, 2 electrons. Well, if you remember what I just said on the last page, hydrogen, 2 pages ago, just kidding, hydrogen can only hold 2 electrons. So the fact that hydrogen has 2 electrons here, that means that hydrogen is happy. All right, that is the second to last step. Check if everybody is happy. If all of the atoms, if all the elements in your compound are happy, then we're good. You're done. You have drawn your structure. If the elements are not happy, we have a little more work, but for group A, these simple molecules, things will be happy fairly quickly. All right. I would like you to try NH3 on your own. Try it now. I'm going to go turn on a light because the sun seems to be starting to go down. But I'll be back in a moment. So just try NH3. I'll be right back to check in with you. And then you've probably seen it already on my CBA. Page 80 practice, you're going to do H2O, SiF4, and NCl3. That will be something that you will submit online, so give those a shot too. But if you want to stop at NH3, just so you can get some feedback, and you can see how things, how that gets done, I will be back in just a moment. Again, I'll leave CH4 up on screen. I just got to turn on some lights. Sit tight. Alright, if you didn't have enough time to do NH3, pause the video. Otherwise, I'll do some explaining. So, NH3, N has the least, it's in the middle. The H's go along the outside. I know that N has 5 valence electrons and H has 1. And you'll notice that I will start to align things so that I know they will look pretty in the end. If you're not at that point yet, it's okay. Do things so that they're kind of dirty and messy, and then clean them up after the fact, right? And then, again, connect the dots. And then check, is everyone happy? So if I look at nitrogen, I see 1, 2, 3, 4, 5, 6, 7, 8. Nitrogen is happy. If I look at hydrogen, I see 2 electrons. It's happy. We're good. That is what NH3 looks like. Now CH4, for reference, CH4 is methane gas. That's what we use in the lab. That's methane, it's a natural gas. That's what we use in the Bunsen burner. NH3 is ammonia. Ammonia is a very common cleaning supply. And yeah, it's a cleaning supply. You know the smell. If you kind of, you recognize it. It's not the bleach smell, it's the other smell. But anyway, that's what that looks like. What I'd like you to do, right? You can do this after the video. You can do it now. Like pause the video, do this now, submit it online, right? These remaining 3, H2O, SiF4, and NCl3. I want you to try those Lewis structures. Give them a shot. Submit those online. Again, full disclosure, right? For the whole year, if you haven't picked up on this, I grade homework based on like, did you do the homework? Do you do the homework and you do it on time and you turn it in, you've gotten full credit. If you do it, but it's late, you don't get quite full credit. Depending on how late it is, will determine how much partial credit you have gotten. But do these questions, submit them. I'm obviously going to go over them very shortly, but I want to give people fair chance to kind of do the work and get some feedback and compare. So take a little time here. I'll get a quick sip of water. Yeah, 30-minute mark. Again, these videos are just going to be longer. I'm going to do kind of like all of these notes, and again, I will do my best to kind of watch back through timestamp stuff. Or roughly timestamp stuff. Probably just go by page. Alright, so H2O. H2O is funny. It's water, obviously, but water is special. It has a lot of unique properties. Oxygen is like our center, and then hydrogens go on the outside. Oxygen has 6 valence electrons. Hydrogen has only 1. Now, it's very possible, it's very likely that you did this, right? And the only reason this is incorrect is because water has like this little asterisk next to it. It's a very unique shape. It has to be bent like the way that I have it in the box right now. Like, this doesn't work. And the reason this doesn't work, the reason we know it doesn't work, is because we know water is very cohesive, right? It likes to stick to itself. This is the reason that water gathers in puddles. Or like if you're looking at your car and you're watching the raindrops go down the window, the drops like attract each other. Like as it goes down, it kind of like pulls drops towards it, or it directs itself towards drops. And the reason for that is because of this arrangement. These electrons here are free, they're just floating. So this side of the water molecule is a little negative, which by default makes the other side positive. Water is polar. It has a negative side and a positive side. And because of that, water will tend to align itself so that they're always attracted to each other. But water is pretty much the only element the only compound that we will deal with that has a super unique situation, right? I know that I drew NH3 the way that I drew it there in the second box. However, you could also do this, and it'd be right, and you could also do this, and it'd be right. And the reason for that is I'm just taking it and like rotating it, right? Rotating it 90 degrees or 180. But it's always 3 H's on the outside, and there's a free pair of electrons floating around. Right? SiF4. Silicon tetrafluoride. Again, I'm skipping straight to the cleaned up version. The thing to watch out for here was that fluorine has 7 valence electrons on its own. And in order for fluorine to be happy, it needs 8 total electrons. So if I look at this fluorine, it has 1, 2, 3, 4, 5, 6 dots and a line, which represents another 2. 6 and 2 makes 8. And then if I look at silicon, it has 4 lines, which is also 8. So we're good there. Similar thing will happen down here with NCl3. N has 5. This was Cl, and I apologize if you kind of had trouble figuring out that was Cl versus Ci3. But this is what NCl3 will look like. Right? I have the 3 chlorines and then a random, or not random, a loose pair of electrons hanging out. All right. Now, the next thing I want is down here, group C, which talks about multiple bonds. Multiple bonds implies that we're talking about not just single bonds, so not just 1 pair of electrons being shared, but 2, maybe 3 pairs, right? There are 3 examples here. Carbon monoxide is super unique. I'm going to use it to do the bottom part, the page 81 there. I'm actually going to add 1 more. I'm going to add N2 as like its own box. Oh, wait a minute. Can I fool this? Hey, there we go. Okay. So, N2 is going to be like its own little box here, all right? So I'm going to look here at group C, the multiple bonds. And my example is going to be this. I'm going to use this second example here, HCN. And the reason I'm going to use this in my example is because there's 1 H, there's 1 C, there's 1 N. They all have 1. I don't know which one's supposed to go in the middle. Kalimlin, you said that whatever there's the fewest of, that's going to be in the middle. All right. If there's a tie, carbon wins. Carbon's a diva. Likes to be the center of attention. It's a little bit of an attention seeker. So carbon is going to be in the middle. I'm just going to line it up the way it is. H on one side, carbon in the middle, nitrogen on the other side. And then I'm going to fill in valence electrons. No, again. Actually, this time, you know what? I'll do this. And then we're going to play connect the dots until everybody's connected to the center point. Then I'm going to count. And if I were to count, if you look at the carbon, right now, carbon only has 6, electrons. Well, that's pretty bad, because 6 is not 8. Well, what do we do if things are not happy? Well, what we do is we continue to play connect the dots until everyone is happy. That's it. That's the rest of the rule. So let's connect these dots and then count again. Well, it's 3 lines and 1 dot. Nope. I gotta do another one. Alright, that's 4 lines. Huh. Okay. That's 4 lines for carbon. Well, that's good, because 4 lines means that it's 8 electrons. And if I look at nitrogen, nitrogen is 3 lines, which is 6, and 2 dots, which is 2. So 6 plus 2. Well, that's 8. So nitrogen is happy too. If I clean this up, which I tend to do, it'll look like this. Now I want you to notice that I put the electrons far away from that triple bond, from that three lines, and that was intentional. Those are electrons. They don't want to be near each other unless they have to. They're stuck next to each other in that triple bond. But those other 2 electrons are free to move, so they're going to move as far away from as possible. Right? What I'd like y'all to do here, right, and this is a page 81 practice, which is, again, also an assignment online. I'd like y'all to do H2CO, CO2, and the one that I gave you, this N2. Ignore carbon monoxide. Ignore CO for a minute, because I'm going to use CO as my example of coordinate covalent bonding. It's a very specific thing. It comes up like carbon monoxide is the example for this, so I'm going to use that there. But H2CO, carbon dioxide, CO2, and nitrogen gas, N2. Try to make the Lewis structures for those. Again, I'll give you a minute here. It's warm. It's a great day today. Great day. Did you give those a shot? You submit that online? Okay. Let's take a look at how you did. Right? And again, I grade homework on completion because I want to know that you're trying, you're doing the work. Checking yourself is the important part. You need to know if you got something wrong, why, or if you got something right, just confirm that you got it right. Right? So there's 1 C and 1 O, but carbon wins. Right? And then I have oxygen, and I have hydrogen, and I have another hydrogen. Carbon has 4 valence electrons, hydrogen has 1, oxygen has 6. Let's play connect the dots. Everyone is not happy. Carbon only has 7, oxygen has 7. If I double bond that, so there are 2 bonds between carbon and oxygen, well, that works. Again, let's clean it up. Interestingly, it will end up looking like this. Now, you didn't have to. You could have left your hydrogens like up here and over here, or flip one of them down, or flip the other one down. That's fine. That's what H2CO looks like. 2 hydrogens, 1 carbon, 1 oxygen. It's a multiple bond because you have a double bond between carbon and oxygen. Right. CO2 is going to be, again, carbon in the middle, double bonded oxygen on one side, double bonded oxygen on the other side. N2 is going to be 2 triple bonded nitrogens. And that's it. Those are our 3 examples there. Right. Now, I will come back to these examples, the ions, probably closer to when we talk about, again, it'll be a little bit from now. Now I'm going to use carbon monoxide to explain what coordinate covalent bonding is, right? Covalent bond in which both electrons are donated by the same atom is called a coordinate covalent bond, right? If you look at the NH3 molecule, the hydrogen atoms are bonded to nitrogen with covalent bonds in which each atom contributes 1 electron to the shared pair. And if you look at your notes example, the reason that we have dots and X's here, the dots originally belong to nitrogen, the X's originally belong to hydrogen. This is the same as what we just had on the last page, right? Instead of doing the lines, they just left the dots there. But those are the same, right? Nitrogen contributed 1 electron, hydrogen contributed 1 electron. Each of them brought something to the table for the pair, right? If you want to make the hydrogen, the ammonium ion, which is you take ammonia and you add an H plus to it. You just add an H to it. H plus is H with 0 electrons. Well, if H wants to add on to this, H doesn't bring any electrons to the table. So when the hydrogen ion tries to come in and bond to this ammonia molecule, ammonia, or really nitrogen, if you look at it, nitrogen has to contribute both electrons to the pair. And this is special. It's called a coordinate covalent bond. It's coordinate because only one side, it's not a true covalent bond because they're not cooperating valence shells. It's one of the atoms was like, oh, you don't have enough. Okay, here. Right? It's kind of like a donation. And the reason this works here is because, look, carbon and oxygen. Well, carbon has 4, and oxygen has 6. And if I do this, they're not happy. And if I do this, they're not happy. But then if I keep going and I try to get like bonded, oh, well, now carbon is happy, but oxygen all of a sudden has 10 electrons, and that's real bad. Right, so what ends up happening is these 2 electrons here, right, both of those electrons become a bond. So oxygen takes it. Oxygen. No, again, I'll re-show what happened there. Oxygen has 4 loose, electrons that are just hanging out, and there's no way to make both atoms happy if each of them continues to contribute 1 electron to the bond. Because of that, oxygen is going to take the 2 electrons that are here on the right side, and it's going to make both of them into a bond and share both of them with carbon. Right? Now, when that happens, if you look, this is 1, 2, 3 lines, that's 6 electrons, and each of them has 2 more spare electrons, which means that when it comes down to it, this is the structure that you see, a triple bond. But one of these bonds is actually one where both electrons came from the oxygen. It's a coordinate covalent bond, right? And it's a very special case. Carbon monoxide is about the only example that I can ever think of. And every year I'm like, oh, Ms. Summerson, I should find another example. And every year, there's no good one. There's not one that comes up frequently. There's not one that's a recognizable compound. So we come back to carbon monoxide every year, right? So there's coordinate covalent bonding. Now, there's a little bit more, but I did do the Redox Lab with your cohorts who are in class now full-time. I apologize that this the PDF looks like it got a little wackadoodle here, because there should be a 6th test tube. No, not good enough. I'm trying to get this autofill box to work. Nope, I think it's too big. What if I do a bunch of small ones? That'll do. Alright, so 6. This is... and I'm just copying this from the top of the next page. Nope, that's wrong. Alright, so when we did this in class, we had every student just had one of these test tubes, and then we crowdsourced it, so we combined data at the end. So we looked, did a reaction occur? And what we found was that in test tube 1, yes, there was a reaction. In test tube 2, there was. 3, there was not. 4, there was. 5, there was not. And 6, there was not. The reaction that we observed in each case was a color change. For one, CuCl2, this compound here, this copper 2 chloride, was a blue solution, and the Fe, which is iron, we just used a nail. So I took a test tube, had the blue solution in it, dropped the nail into it, and the very bottom of the nail became this kind of rusted out color. Right? So there was a very clear color change. When we did the same thing with the blue, but we put a piece of zinc. Now zinc is a kind of not super shiny, a somewhat dull silvery color. It's actually the color of a nickel, as you would have it. But zinc, when zinc was placed into it, it got almost like charcoal. It looked like, not like jet black, like shiny jet black. It's like a matte black charcoal look to it. So it very clearly changed color, more than just being wet from being in a solution. Right? The last solution that we saw, the zinc, so iron nitrate, FeNO3 is an orange looking solution. It's just mixed with water. And we put that kind of dull-ish silvery piece of zinc in there, and it came out almost shinier. It was not quite gold, but it was a gold twinge. It was like a gold shade, but it was definitely a different color. All of the other ones, in two of them, were copper, and then the nail went into another one. But in all of those, the copper maintained its original color, and the nail maintained its original color. Now, because there was no reaction observed, there are no products to be had. This lab was a redox review, and if you remember, there was a certain kind of reaction that would always, 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 always be a redox reaction. That type of reaction was a single replacement. So, single replacement reaction for 1 means that our products would be copper and iron 2 chloride. Here, for the second one, it was going to be copper and zinc chloride. And for reaction 4, it was going to be iron and zinc nitrate. So yeah, that's what those look like. That was the data from the lab. The next thing that we had to do was answer some questions. And again, I don't know why this got all wackadoodle. Now, question number 1 asks you to list the metals in order of increasing, reducing strength. I want to like replace this with something. I don't want you to think about it as reducing strength. I want you to think of it as reactivity. Right? If you look at this in terms of reactivity, list the metals. So the metals were these things here, the actual solid that we put in. And if you look, iron reacted 1 out of 2 times. Zinc reacted 2 out of 2 times. And copper reacted 0 out of 2 times. So if I'm trying to do this in terms of increasing reactivity, well, that means that it was copper, and then iron, and then zinc, because copper reacted the least, iron reacted kind of the middle, and zinc reacted the most, right? Increasing reactivity, and it turns out that's the same question. Increasing reactivity is the same as increasing reducing strength, right? Now, question number 2 is a question that you already have the answer to. Check Table J. Go to your Table J, and you should have a note there. Table J is the tall table. It's the activity series. And it says the higher a metal is on Table J, the more active it is. What does this mean in terms of reduction and oxidation? You should already have written down that the most active metals are most likely to go through oxidation, and the less active metals are more likely to go through reduction. So that's what it means. You already have the answer to number 2. Make sure you write it down. Number 3 is the tricky one. Number 3 is the tough one, because I want you to write half reactions, which means you need to remember what a half reaction is. You're only going to have 3. You have to do it for number 1, number 2, and number 4, because that is where you observed reactions. I will do the first one with you. That will give you a template to follow for the other 2, right? So, in question number 3, the first reaction that we saw was the iron nail in the copper 2 chloride turning into copper and iron 2 chloride. Now, the interesting thing is that even though it looked like the nail rusted, what really happened was that the nail was plated with a very, very small, thin layer of copper, and that's why it looked like it rusted. Rust and copper have similar shades. So this copper solid is like adhered itself to the outside of the nail. What was even more interesting is that you could actually wipe it right off. It was so thin of a layer that it would just come right off. Now, in order to do half reactions, I need to identify what elements went through a change in charge. What elements went through oxidation and reduction. So elements that are hanging out on their own have a charge of 0. Chlorine, when it comes second, is negative. It has to have a charge of -1, but there are 2 of them, so this copper has to be +2, this iron has to be +2. Right. My half reactions only worry about things that change. So iron changes from 0 to +2, copper changes from +2 to 0. So that means that iron with 0 charge turns into iron with a +2 charge. Well, that's great for mass, but it's lousy for charge. I need to add 2 electrons to the right side so that the charge on both sides is 0. The charge on both sides matches. I also need to indicate whether this is oxidation or reduction. Because the charge goes up, I know that this is oxidation. The other thing that took place was that copper went from a +2 charge to copper with a 0 charge. Well, since the charge is going down, the charge is being reduced, I know that's reduction. Also, because it's reduction, I know that electrons need to go on the reactant side. They need to go on the left side. Again, if you try to add electrons to the incorrect side, you simply will not be able to match the charges. If I go down from 0, I'm never going to hit +2. But if I go down from +2, I will eventually get to 0. That's how I know how to do that. All right. For number 3, you have 2 more reactions to do. We had 2 other single replacements. Here are the reactants for one, the products for that one. Here are the reactants for the second, the products for that one. You need to do the half reactions and just label them. One is oxidation, one is reduction. Oxidation is the one in which the charge goes up. Reduction is the one in which the charge goes down. Right? This lab also has an assignment, right? It should be up already. Now, I am now getting into being a little bit ahead of the kids in class, but that's okay. This will hold you over until next Wednesday. So these assignments won't be up yet, but if you continue to check daily, you will see when the assignments go up, and you'll be able to complete them because you will have these notes, and you can reference them. You'll have the examples. Some of the examples will be in the orange book, so just know that going into it. But the last bit of our little bonding section here is, so we talked about ionic bonding, covalent bonding. We talked a little bit about creating the Lewis structure for simple molecules, the Lewis structure for molecules with multiple bonds. Again, I will double back to the ions and the rules for ions, but right now, covalent bonding is much more interesting, and covalent bonding has a couple more relations to what we call molecular polarity, right? We talked a little bit about polar and nonpolar for an individual bond, but the whole molecule can also have a polarity, and we will much more frequently discuss the polarity of the whole molecule, which is why I talked about the example of like the North and South Pole for the Earth, as far as having poles, right? Determining the polarity of a molecule is not the same as a bond. I don't worry about the polarity of a bond so much, but we talk about the polarity of a molecule quite a bit. Whether or not a molecule is polar depends on whether or not there is symmetrical distribution of charge. Now, you hopefully remember from like your art classes or like elementary school, symmetry is there is like a mirror image, right? This way, or a mirror image this way. The way that we look at it, you need symmetry in both directions. So you need up-down symmetry, and you need left-right symmetry, right? So if a molecule has poles, and then because it has poles, it has an unequal charge distribution, it is, I'm gonna use a different word here. I'm gonna use asymmetrical, which just means not symmetrical. It is a polar molecule. If it does not have poles, thus it is symmetrical, then it is a nonpolar molecule, right? And the reason I switched to asymmetrical and symmetrical versus unequal and equal is because I have an acronym for this, right? I have a little mnemonic for this. It's SNAP. S-N-A-P, which stands for symmetrical is nonpolar, but asymmetrical is polar. The reason we needed to do the shapes and stuff before is because this is where we're going to use it. All right? If the shape of the molecule is symmetrical both ways, so it's up-down symmetrical and left-right symmetrical, then it's nonpolar. So CH4 is the prime example of a nonpolar molecule because it is the same up and down. Like if you did a mirror image of it up-down, if you do a mirror image of it left-right, it works. You don't need to worry about the shape of the letter. You just need to, like, carbon is C, right, is symmetrical up-down, but it's not symmetrical left-right. I'm not talking about the shape of the letter. I'm talking about the shape of, like, the entire molecule. If you were to look at NH3, right, it is not symmetrical up and down. The top part has 2 electrons, the bottom part has an H. That's not symmetrical. It's polar. And what that means for ammonia, if I'm looking at it, it's fine. It's fine. If I'm looking at it, if I'm looking at ammonia, then I know that this side is a little negative because it has electrons. Electrons are negatively charged. Those electrons are not shielded. They're not like in between two things. They're just hanging out. They're on the outside. That side is a little negative and the other side is a little positive, right? So it has poles. It has a negative and a positive pole. The prime example, the best example of a polar molecule is actually water, right? If you look at water, this side of it is negative, the side of it is positive, and again, that was why I said earlier that water has all of these interesting and strange properties. Because it's polar. It's because it has these oppositely charged ends that will attract each other, and it's also why it's very good at dissolving so many things, but you know, we'll get more on that when we talk about solutions. It's a little bit later. All right. Determining the charge of a pole. The charge of a pole, the end of the molecule, is technically determined by comparing the electronegativity. Electronegativity values of each atom present in a bond. Technically, you have to do it for each bond. Realistically, you can look at it just by the shape. Wherever the free pair of electrons exists, that's going to be the negative side, right? So I can just look at these. I can look at these molecules. This is nonpolar. It's the same all the way around. This is polar. It has 2 negative charges up here that are just hanging out. This is polar. It has negative charges here and here that are just hanging out. This is nonpolar. It has negative charges all over the place, but they're evenly distributed. It's symmetrical. This is nonpolar, right? It has negative charges that are hanging out. So again, you can tell by the shape. You can also tell by the formula. If you look, this is even, and this is even. They were symmetrical. They were nonpolar. 3 is odd. 1 is odd. Oh, well, yeah. 1 is odd. 3 is odd. The odd ones, those ones have all been polar. So there are other ways to tell, but we have that going for us. Now, I'm not gonna, again, this is a little more technical. And it's a little more, there's a little too much nuance going on in there. The big thing I'm worried about is that you can tell the polarity of a molecule by the shape of the molecule. If it's symmetrical, it's nonpolar. If it's asymmetrical, it's polar. That's the snap thing, right? Last thing I'll talk about here are intermolecular forces, or IMFs. Right. Now, IMFs are the attraction between molecules, not between atoms. Atoms are held together because electrons, right? They're either sharing electrons so they're close, or they're attracted to each other because they are positive, negative. But we're not talking about inside the molecule. We're talking about between two separate molecules. So I have like a molecule here and a molecule here. What's the force between them? Is it being held together strongly, or is it just like, I could be near you or not, right? But they are known as intermolecular forces. The strength of an IMF is what determines boiling point and melting point. They determine phase changes. If something has strong intermolecular forces, their molecules are held together very tightly, well, that means the melting or boiling point are also going to be high, because it's going to take a lot of energy to take them apart. Right? They're also related to mass, and this is kind of sort of like gravity, right? The larger a molecule is, the stronger IMFs. That means you're going to have higher melting point and boiling point. There are three kinds of IMFs that we'll talk about, and they're the three titles. Dipole forces. Hydrogen, I want you to be careful writing this. Bonding, those quotation marks are intentional. And London dispersion forces. Now, I'm going to break these down into kind of simpler versions of what you see. Dipole forces are strong. When covalently bonded atoms within a molecule do not share electrons equally, not equal. Unequal means poles or dipoles are established. We call them dipoles because there are always two, right? You have a positive and a negative. You have a north and a south. You're never going to have one pole. But poles are established. And when you have poles, you have a positive, negative, opposites attract. They're attracted to each other by what we call dipole forces of attraction. For short, we just call them dipole forces. But they're strong. Right. And again, this has to do with electronegativity, but just to fill in the blanks, opposite ends are attracted to each other, and thus a dipole force is present. Now, I want you to do this. Quotation marks around bonding. But it's the strongest. Right? Hydrogen bonding is a very special case of dipole forces. So it's like dipole forces are strong. Hydrogen bonding is even stronger. It's just a special case of dipole forces. Spoilers, it involves hydrogen. It's called hydrogen bonding because originally they did actually think it was a bond. It was that strong. It was so much stronger than a traditional dipole force. But it is an IMF, right? In hydrogen bonding, the hydrogen of one molecule will come near a neighboring molecule, and it creates an unusually strong force of attraction between the two polar molecules. And this is the strongest intermolecular force that exists. So that's why I just want you to remember, hydrogen bonding is the strongest. So dipole forces are strong, hydrogen bonding is strongest. Don't worry about the pictures are a little more confusing than they're worth, and we're always changing it. We've gotten rid of a lot of pictures. We'll probably get rid of these ones. London dispersion forces are IMFs that exist between two nonpolar molecules, and because of that, they are weak. LDFs are in fact the weakest IMF. The melting and boiling point of nonpolar molecules will increase with increasing mass, so they are greater for bigger molecules, but they're still really weak. LDFs are very weak. LDFs are what hold sugar molecules together, which is why it's pretty easy to melt sugar. But yeah. Alright. There are some bonding questions here. Of these questions, this question, this question, this question, this question. Those 4 questions are 4 questions that I would like you to answer. Now, this assignment will not be up yet, but when it goes up, it will be titled page 84. You will be able to submit it. All right. There will also be one assignment out of the orange book, because this is like a section, right? Bonding is a section, which means quiz coming up. Won't be until middle of or late next week, so Wednesday, Thursday, Friday next week. But that is all the stuff. Again, there's probably one more lab. It'll be in the next video. The next video I think will have 2 labs. That's okay. But there are the notes, here are the examples, here are the diagrams, here are all the blanks that you will need here. Please email me if you have any questions. Schedule a Zoom if you need to. I know that this was long, but again, I will do my best. I'll try to timestamp stuff. I go roughly in order, so like know that. But yeah, if you have questions, please email. Keep up with the assignments. I know that it's been a little confusing. It will get better after this week, right? So it will make more sense. You will be a little more aligned with things after this week. Next Wednesday, look for the next video. Probably be about the same length. But again, you can break it up day by day. It's an hour-long video, but you break it up day by day. It's only going to be between 10 and 15 minutes a day. So, which is about the same as I had before. Anyway, that's what we got. Let me know if you have questions. Otherwise, I will see you in the next video. Take care, kids.